Alright, so part 3 of our optimization problems. Let's go ahead and jump right in. This is one of those classic problems that's in just about every textbook. Let's go ahead and look at number 7 right here. A piece of wire 40 centimeters long is to be cut into 2 pieces. One piece will be bent to form a circle. The other will be bent to form a square. Now this is a two-part question. The first one says, find the lengths of the 2 pieces that cause the sum of the area of the circle and the area of the square to be a minimum. Okay? So let's go ahead and let's see if we can fold that so that we can actually keep an eye on it while we're working on this. Okay? Now, what happens here is that if you're going to cut this thing, which is 40 centimeters long, part of it is going to be used for the circle, part of it's going to be used for the square. You know that one of those lengths is x, and one of those lengths is 40 minus x. Okay? So let's go ahead and let's use the 40 minus x, okay, for the square. And let's use the x length for the circle, okay? Because here's the thing. If x length is for the circle, I actually have to get back to the radius in order to go and find the area, okay? So remember, circumference is equal to 2 pi r. Area is equal to pi r squared, okay? And so what happens here in the circle is I need to put x is equal to 2 pi r, so r is equal to x over 2 pi, which then becomes area is equal to pi times x over 2 pi squared. Okay, so the area of the circle is going to be basically 1 over 4 pi times x squared. Okay. Now, if you had tried to do that with 40 minus x, it just would have been a little bit messy. Okay. Now this one is a little bit easier in terms of how you go from perimeter back to area. You know that if this is the perimeter, then each side of a square is going to be equal to 10 minus x over 4, and therefore the area of the square is 10 minus x over 4 squared. So if you want to find the maximum and the minimum of their cumulative area, okay, what you need is you need to go ahead and add those 2 areas together. Okay? Therefore, area in general is going to be area of the square plus area of the circle. Now this, let's go ahead and multiply this out. That's going to be 1/16 x squared. Now, of course, the middle term is going to be 2 times these 2 times each other, so it's going to be minus 5x, right? Because 10 times 1/4 x is going to be negative 5/2 x times 2 is minus 5x plus 100, and that's the area of the square, plus 1 over 4 pi x squared. Obviously, those 2 quadratic terms can be combined, and I have 1 over 16 plus 1 over 4 pi as the coefficient of x squared minus 5x plus 100. And let's go ahead and take that derivative. I get 2, 1 over 16 plus 1 over 4 pi x minus 5. And of course I need to set that equal to 0. You're going to get an irrational number. I mean, that much is clear, okay? The trick is to figure out what it is. Is it the maximum or is it the minimum? Well, you know, let's go ahead and find it first of all. So I have x is equal to 5 over 2 1/16 plus 1 over 4 pi. And let's go ahead and find that decimal approximation. So 2 parentheses, and we'll do fractions within fractions, and that'll just be all sorts of fun. 1 over 4 pi. Okay. Okay. And so what we have here is about 17.6. Okay. 17.596. So that's 17.596. Now, you have two choices, okay? You can evaluate whether this is the maximum or the minimum using a first derivative sign chart, okay? I mean, obviously you can reason it out. But you can also do it by the second derivative test. We've already talked about the second derivative test, right? And I know that the second derivative, since the first derivative is linear, the second derivative is just going to be that coefficient, which of course is positive. This means that while I'm in the midst of this particular critical value, it's concave up. That is the x value where you cut that 40 centimeter, is it 40? Yeah, 40 centimeter piece of wire in order to maximize it. And of course the 17.6 needs to be used for the circle, and 40 minus 17.6 would be the square. Okay, well, if that's the minimum, what about the next question, which asks us about the maximum? How could you make the total area of the circle and the square a maximum? Well, if there's only one critical value inside the interval, then the maximum must be at the end of the interval. The scenario has set up such that x, your input variable, can be anywhere between 0 and 40. So if the minimum is somewhere in between there, the maximum is at one end or the other, meaning using all of it for the circle or using all of it for the square, and you would simply figure out using all of it for the circle would give you what area, using all of it for the square would give you what area, and one of those is going to be your maximum value. Okay, so basically it goes back to 4.1, where we're not necessarily looking at a maximum or a minimum, finding extrema just on negative infinity to infinity. We have actually been set up such that we're finding maximum and minimum values on a closed interval, and that's significant. Okay. Now, let's go ahead and look at another classic example. This is one that is not going to be fun for some of you, but it is a really significant one. In fact, there's a really neat, or some would probably say hokey, a really neat video that I'll try to remember to link when I send you these videos about a calculus teacher who has a dog and how Elvis knows calculus. Elvis being the dog, of course. Let's go ahead and look at number 15 right here. A person in a rowboat 2 miles from the nearest point on a straight shore. So he's out here in his rowboat, okay, and he's 2 miles. That's sort of the perpendicular to the shoreline. So if the shortest distance between 2 points, straight line, so the distance he is out from the shoreline is from that perpendicular. A person in a rowboat 2 miles from the nearest point on a straight shoreline wishes to reach a house 6 miles farther down the shore. If the person can row at a rate of 3 miles an hour and walk at a rate of 5 miles an hour, find the least amount of time required to reach the house. How far from the house should the person land the rowboat? Okay. Now, what's going on here is basically, you have 3 options. You can aim the rowboat straight at the shoreline and then walk the entire 6 miles. You can aim the rowboat right at the house and go all the way to the house in the rowboat, or you can aim it somewhere in the middle, and it actually winds up being somewhere in the middle is going to be the best scenario. Okay. Let me go ahead and fold this paper so we can keep an eye on it while we're doing this. Now I'm going to go ahead and start labeling this so we can move forward. It asks us how far from the house the person should land the rowboat. So I want my x value to be the distance from the house, meaning that this right here is 6 minus x. Okay? Now that makes things a little bit difficult, okay? Because here's what we're doing. We want to minimize time. Okay? It says, if a person can row at 3 miles an hour and walk at a rate of 5 miles an hour, find the least amount of time required. Well, finding the distance is easy. Obviously, that distance is x, and obviously that distance can be arrived at by Pythagorean theorem. But I know that distance, okay, I know that distance equals rate times time. And therefore, I know that time is equal to distance over rate. So what I need to do is I need to find a way to represent that distance with an x, like I said, by Pythagorean theorem, and take those distances and divide them by their respective rates. And then I need to go ahead and I need to minimize that. I need to optimize it, okay? So I know that the total time, right, is going to be equal to the time in the rowboat plus the time walking. Okay? Well, let's find the rowboat part first because that's a little more difficult. I know that 2 squared plus 6 minus x squared is equal to the distance rowed. Okay? So everything that's walking, I'll put with a subscript w. Everything that's rowing, I'll put with a subscript r. Okay? So that winds up being 4 plus x squared minus 12x plus 36 is equal to d sub r, or x squared minus 12x plus 40 is equal to d sub r. Okay? Now, let's go ahead and get rid of, I think we understand the scenario here. So I know that d sub r, okay, if he's rowing at 3 miles per hour, this is basically miles, right? So his t sub r is going to be x squared minus 12x plus 40 miles over 3 miles per hour. Okay, so that actually winds up being x squared minus 12x plus 40 over 3, and the units now is hours. And you can go ahead, I suppose, and actually, turn that into minus 4x plus 40 thirds hours, okay? And of course, the other one, the walking time, is just going to be x over 5 hours, okay? Well, that winds up turning this, of course, when you combine them. So we're going to go ahead and say, well, the total time is equal to 1/3 x squared minus 4x plus 40 thirds plus x over 5. And we'll go ahead and simplify that again. So if I have negative 4, that's negative 25ths, plus 1/5 is negative 19/5 plus 40 thirds. And the total time, if I go ahead and take the derivative, is going to be 2/3 x minus 19/5. Set that equal to 0, and I'm going to get 2/3 x is equal to 19/5, or x is equal to, well, what's 19 times 3? Okay, well, it's 57, okay, over 10, and therefore 5.7 miles, okay? So we need to aim the boat 5.7 miles from the house. So almost straight in, but not quite. And what that means is that the rate at which they walk is fast enough that you're not going to want to spend much more time rowing than you have to, okay? So if this whole thing was 6 miles, you're really aiming right about there. Not here, but there, okay? That winds up minimizing the amount of time spent traveling to the house. That one's a little bit difficult because it's not distance, okay? And the difficult part is that part right there. Figuring out that we need to go from this formula to this formula, and each distance needs to be divided by its respective rate in order to represent hours in terms of our variable x. Okay, I may do one more video on optimization because I kind of dropped the ball and didn't do any of the Mickey Mouse products and stuff like that ones. So I may just do a short video on a couple of the really easy ones, and hopefully that'll round out our knowledge of optimization, not only for now, but of course for May. So be looking for that. Okay? See ya.